Welcome back to part 3 of Introduction to Hydraulics. In this particular module, we're going to take a look at the components that make up a hydraulic system. We're going to look at open loop circuits, discuss closed loop circuits briefly, and hydrostatic drives. We'll get into those further on as we get into valves and proportionality. Discuss general hydraulic components, their purposes, and their functions, and discuss hydraulic circuits and pressure valves. Again, just at a general level, we'll get further into hydraulic circuits and pressure valves in the units to come when we get into schematics and different components. This is more just the 20,000 foot view of what we're looking at. We're going to discuss circuits to control the speed of cylinders. So speed control is, as we've mentioned before, very important in a hydraulic circuit, especially if you're applying a lot of force and you're bending a metal or pressing something and forming it in a forge. You need time for those processes to happen. Otherwise, you can have breakage and shattering that can take place. Okay, so an open loop circuit is pretty much the standard for any equipment that is set in place. Open loop circuits are most commonly found in industry. They have a large reservoir, and this reservoir, as I mentioned before, has 3 times the fluid that you will find at any given time in the system. So really there's, 3 parts of the fluid are in the reservoir cooling down and having impurities removed by settling and by these baffles and inlet filters. And again, the reservoir is there as a cooling chamber for the fluid. It may have a cooling fan attached to it with a little pump inside that will actually circulate the fluid up to a heat exchanger, which will then dump heat out of the fluid if it's not cooling down fast enough. You can also have heaters in reservoirs if the fluid is experiencing cold ambient conditions like -35, -40 degrees. Fluid sitting around in the bottom of containers will get quite viscous, and it may not be circulating the entire volume of the fluid. These systems weigh a lot because of the fact that you have all of that fluid sitting at rest, and as a result, they're best used for stationary equipment. You can have these quite often in my world, the wind turbine world. You'll have these type of open loop circuits inside the nacelle for pitching the rams on the blades to pitch the blade position. Occasionally you may have a hydraulic yaw, but those have pretty much fallen out of favor because they are messy and subject to leaking and vibration and things like that. So here's a simple open loop schematic. Here we can look at these basic symbology. We'll get more into the symbology as we go into the course in the next few modules to come. But suffice it to say now, is an indicator of a motor-driven pump. The reason I know it's a pump is the arrow is pushing the fluid out towards this T or this X intersection, 4-way intersection here with a pressure gauge on top of it. This is a pretty standard setup, and if it's a motor, the arrows would point in that it's inputting power. So this is outputting the fluid flow, and the flow is flowing this way. This is a pressure relief valve. On top here, you see this squiggly line, which means that it has a spring set on it, and that this arrow indicates that it is user operable. So the user can actually determine the set pressure of the system. And again, I mentioned that this is a safety device. You don't want it going off all the time if it doesn't need to. You have this dotted line here, which is an interesting line. It's called a pilot line. These solid lines are called process lines. Process lines are lines that contain most of the fluid, and that's what's doing most of the work. A pilot line is simply that. It just gives a small signal to the inner components of this device, in this case, a normally closed pressure relief valve. If the pressure grows too high on this side because of load coming off of the system, the pilot line will back up and will open this valve, allowing more fluid to come out and back to the reservoir. As soon as that pressure equalizes, of course, the spring pressure takes over, slams that shut. Another thing you can find with you have PRVs, pressure relief valves, going off all the time is you'll have a chattering sound when you move your actuators. Pop, 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 pop. That's telling me that there's a problem in the system. You may have a restriction that's causing that pressure. A lot of times if you'll get dirt inside a fitting, especially in one instance, we had food processing equipment that was all linked together hydraulically. So when you put another conveyor on, you simply just added another power pack and connected the lines to the header. However, because of dirt and the environment, eventually you'd get enough of the mud in the lines that it would start to affect pressure and speed and flow down the line, and your pressure relief valves would start going off at your main pump. So these are all signs from being in the field of what happens when. So a closed loop circuit, this is more something you will find on a hydrostatic drive and drive motors that are hydraulically controlled. We have a main pump here, and you see that this pump is bidirectional. It can go either way. The reason I know that is because there are two arrows, one going this way, one going that way, and it's also a bidirectional motor. You have a drain from the case. Now what this does is the drain from the case allows some bypass fluid to lubricate the motor's seals and bearings and what have you with the hydraulic oil rather than have them fetch up, right, or seize. Same thing with your main pump here. And this is an electrically driven machine. And you have a charge pump here. So this charge pump would charge the system prior to its running. And once it's charged up, this line will come open. So when this charges up, eventually the pilot line will send some fluid down if it gets too high to the spring pressure and return the flow, dropping the flow back on this. But in the meantime, this flow will push out of this and this check valves. These check valves, as you see, are a V with a ball in it. Now, generally, they have a spring inside of them, and the spring is a preset pressure. So if the pressure of the fluid is greater than the spring pressure pushing down on the ball, the pressure of the fluid wins. So as this pump comes up to speed and pressure, it charges the system, driving out any of the air that may have leaked in. On motors and pumps, you have the real mechanical world meeting a sealed fluid environment through a seal. And the seal, unfortunately, can be an issue. It can actually leak. And as a result of that, things need to be lubricated. And some machines, hydraulically operated, are just messier than electrically operated machines. In this case here, the reservoir is approximately 3/4 of the charge of the pump capacity. And it's compact and lightweight inside. It's used on mobile equipment. And if you've seen a ride-on lawnmower for large parks and things, this is the type of drives they have in them. And you literally will change the direction of the control valve to change the direction of the pump and the motor. Quite ingenious. Very simple system, very robust. You will get properly maintained millions of hours, hundreds of thousands of hours out of these machines anyway. Okay, so in this particular situation here, we have the major components of an open loop system. We have a motor and a pump, an inlet strainer. This is our reservoir down here with our return line filter, which will filter out any impurities that it's picked up during its travel through the system. That's pretty common. These are wearable parts. If fluid is getting out, air is getting in. Even if it's just seeping or sweating, you will still have some ingress of moisture and some outflow of fluid, and dirt will travel in between. Flow control valve here. Now, flow control valve controls speed, but not pressure. There will be a pressure drop across the flow control valve, but it's negligible. As the speed is equalized, the pressure drop across it is minimized. So we don't, even though it is a bit of a parasitic load, we don't count it too much. All right, so the directional control valve, and this one here is a spool valve. This is a spring return spool valve, and it has two directions. It can make the fluid flow in this direction, or it can make the fluid flow straight across, crisscross, or straight across. And in a lot of times, these ones will have a cycle back to the tank when not in use. So the fluid is constantly being circulated, filtered, viscosity is maintained because it's always moving. A lot of advantages to keeping the system moving. The cost of it is going to be the cost of your electrical power, right? So the fluid is the blood of a hydraulic system. It does many things, just like the blood in your body. It acts as a coolant, carries heat back to the reservoir or cooler where it can be dissipated. It provides the medium to transfer of power. It lubricates. It's extremely important. Its viscosity must be as specified in order for it to work correctly. One of the biggest problems with hydraulic systems, any hydraulic system, is incorrect oil use or the wrong type of fluid use. A lot of folks like to go with synthetics because they hear synthetics are the best thing since sliced breads in terms of oils. And normally they would be right. They keep their viscosity over a wide range of temperatures. They are almost oblivious to thermal breakdown. They're hydrophobic, which means they reject water. They don't absorb water. And none of these things can be said about mineral oil. However, a system that's been running on mineral oil with booms and has never ever leaked and has been dependable for years and is producing great power, you drain the oil out of that and put it with synthetic oil, it will start to run very badly, very quickly, and leak everywhere. A lot of the deposits from the natural fluids, from the mineral oil fluids, get into all those little places where they need to be. As the machine wears, it's almost like that crud just kind of goes in those little crevices and just makes the machine function so much better. So beware of that. If you're totally rebuilding a machine, that's a different story. If you're putting in new seals and new bearings and perhaps new bushings and you're checking your clearances again, I mean, by all means, go and use the fancy oil. But if it's an older machine and it's been running fine on SHC 90 mineral oil, I wouldn't change it. Let her pound. Word from the wise. Okay, conductors. Conductors are pipes or tubes. Now, which is it, a pipe or a tube? Well, that's a good question. If you're looking at the inside diameter measurement where the fluid flows, well, then we call it a pipe. So a 2-inch pipe has an inside diameter of 2 inches or 50 millimeters, right? A tube is the outside diameter. So if it's a 19 millimeter tube, that's 19 millimeters on the outside, it may be as thin as 12 millimeters on the inside, right? Conductors are important because the pressures are typically 3,000 PSI or plus, so 3,000 pounds is, many atmospheres, many bar, over 200. You'll notice in the notes package that there is a conversion factor there for all of the PSI measurements and bar measurements. I will apologize. The last time I was presenting this course was to a bunch of folks that don't understand System International units, and I had to move everything over into pounds per square inches. So I've left the appropriate conversion sheet in your notes package for this particular episode. Okay. Now here you can see that a connector is a dot and a crossover is just a jump over. Sometimes they don't bother jumping over, there just won't be a dot. So that will indicate very much like an electrical circuit that it isn't actually connected. Reservoirs, these are very simple reservoir schematic symbols. It's just 3 sides. Sometimes they'll have a 4th side and a little spigot that comes out of the top of it. That could indicate a covered but vented to atmosphere reservoir. This is a pressurized reservoir that you'd find on a hydrostatic machine a lot of the times. They don't have a vent on them. They have a certain amount of fluid, and that's what they have in them. A line terminating below the fluid level and a line terminating above the fluid level. So this would be a discharge line. This would be a suction line, more than likely. A pressurized vessel, a pressurized reservoir is not vented to atmosphere. So it may have a higher pressure in it than it will definitely have a higher pressure in it than a vented reservoir, but the entire system of the hydraulic pack itself may be quite high pressure and should be approached with caution, right? I know that the sealed systems that are inside the pitch rams of 3 megawatt wind turbine generators carry 300 bar, 300 atmospheres worth of pressurized fluid. Now, it's a closed loop system, so there's only 30 liters in that system when it's shut off and in place, but that system is enough that if the power is lost, it can revert to its park position on the rotor, which is to snap them 90 degrees out of the wind. And it can do that within a couple of seconds. Now, those blades are upwards of 60 meters long and weigh 15 metric tons. So that's a lot of weight or sail area that's being taken out of the wind in a hurry. So there's a fair amount of pressure there. Even though it's only a small amount of fluid, it is charged to such a high degree. Inlet filters are strainers and return line filters. So the casing is indicated by a diamond shape, and there is a dotted line across it indicating the filter element. Now, some of these will have little shoulders on them telling you that it's a replaceable element. Some of them will have part numbers on them telling you that it's an entire replaceable unit that you unscrew and screw back in, very similar to any oil filter. Okay. Now, the inlet filter's job is not to provide very much filtration. It's designed to keep stuff out of the pump. So if there's any larger pieces of metal or anything like that that could get into the pump or into the pressure relief valve or into the sensitive bits that are coming right out of the gate, it makes sure that it doesn't get in there. It's generally a mesh, fairly fine, but not too fine, because you don't want to have a problem with suction across that inlet filter, because you can have low flow to your pump, which can cause cavitation, which is a deadly hydraulic fault. Actually, cavitation is one of the worst things you can do to your system. A return line filter is installed after the actuator, and that is after the fluid has been pumped and through the pressure regulator and through the speed reducer or all of the riggings that it's been to right up to the actuator, and then is going back to the reservoir. It will have picked up any contaminants in the system by that point, and it's a good place to capture any type of contaminants. Now, on larger hydraulic systems, in the wind turbine world, we have quite large transmissions, hydraulic transmissions. The one I'm thinking of, D-Wind, is basically a torque converter, very much hydrostatic drive, and the hydrostatic drive output is to the generator, and the input is from the main bearing or from the mechanical gearbox. Its job is to smooth out all of the bumps from the wind and the grid, and the fluid in the transmission does a wonderful job of it. The only problem is the oil must be kept super, super clean in order to do that work. So the oil is monitored by a SCADA system, which is a solid state control system inside the turbine that looks for metal, looks for water, looks for dirt, looks for other oils, looks for any source of contamination whatsoever that could be an issue when you go to start the machine up or run it. And we'll send you a fault code. We don't usually install filters in the feed line. And at this point, I'd ask you why. Any filter, to cut it short, is a barrier. Filters can plug. So we could have a dramatic pressure drop across a filter, and that could lead to a filter failure because they're not high pressure devices. A lot of filters will actually have a bypass valve that if the filter element does get plugged, that the fluid bypasses the filter so it doesn't rupture. But it would not be a great way to do it. You would be losing a lot of power, and there would be a lot of wasted transmission of energy and heat into that filter. Pumps. Pumps are what make the fluid flow. They do not provide pressure. Now, this is a single direction outlet pump, drive shaft, inlet, casing, and the direction of rotation is shown, as well as the direction of fluid flow. Okay. The hydraulic system is designed to restrict the flow that is provided by the pump, and that's what builds your pressure. There are several types of pump, but they all work very similarly. Most pumps in a hydraulic system, because the oil is thicker and more viscous, tend to be gear pumps or not perfect seals like you would find in a water pump. Okay. Generally, because of the amount of work they do, there is an awful lot of lubrication that has to happen and heat transfer. So we wouldn't want to have a really tight casing like you would have on a water pump, because the pump would fail. There is a fluid intake from the inlet side. Generally, if it's a gear pump, it would go around both sides and then it would spin it out the top. If it was a volute pump, it's using centrifugal force, it sucks it into the middle and it slings it out to the outside, where it's then directed through the volute and out into the rest of the system. So a maximum pressure relief valve is a pilot operated valve. They're required in a hydraulic system. You may have a sealed unit in a hydrostatic system that you cannot adjust and has been factory set and has the paint on the screw on top of it. Yes, if there's paint on the screw, don't take the paint off the screw because you void the warranty. And some of these pumps can be worth, I'll give you an idea. The pressure relief valve for the hydraulic vane system on a GE G5 natural gas compressor is worth $380,000 US. And there are 3 of them. And they are all factory set and calibrated. And you do not touch them, or you void the warranty on the 5 megawatt, $7.5 million US machine. Do you understand me? So, if you ever run across paint on top of a screw that looks like you can adjust it, do not adjust your set. That's extremely important. There's a story behind that. Perhaps one day over a Pinchot, I will let you know about that one. Okay, here's what happens with this system. Here we have a tee-off coming off of the system from the pump. So the pressure going to the system and the pressure coming from the pump will all be the same, and we'll be on this board-on-tube pressure gauge, which most systems require by law. The inlet to this closed valve pumps against a valve wall, so there's no way for the fluid to go. So the pressure will back up. Now, if the pressure reaches the same amount that this spring has been set to on the adjuster, if it's not painted, okay, that fluid will push this particular gallery for that oil to go through and allow it to go back to the reservoir. This makes sure that the system pressure does not go beyond a set point. I'm never going to say this too many times. You don't want your pressure relief valve set to the same or close to your operating pressure that you expect to get. Otherwise, you will have chattering and power loss, And yeah, it just won't work well. It's a safety device after all. If you need to adjust the pressure, we'll get into that. There are valves designed to do that, that will use that pressure and regenerate it back into the circuit softer or divert it, but they won't hammer on, hammer off, which is exactly what a maximum pressure relief valve does. It's a water hammer was the term that we use for that, and it's very hard on components. A directional control valve. Now, directional control valves can be manually operated, electrically operated, operated by hydraulic pilots. There's many different ways you can use it. Now, they're all very much the same, and I just love the schematics and the logic representations in all of hydraulics because they make sense. P is from the pump. T is going to tank. A is going to the A side of the cylinder. B is to the B side of the cylinder. Right now, what happens is when it's in one position, it goes from P to A, fills up the back of the cylinder, drives it this way. And the other is going from B to tank, so the fluid is pushed out of this side of the cylinder and back to the tank. When I engage this, the pressure goes into B and drives the cylinder this way. The A will then take that and take it back to the tank. Now, a lot of times these will have a middle position where literally it will just send it back to the tank through the filter. Those are used on systems where it's on, off, on, off, on, off all the time, and there may be a high degree of dirt ingress, and you may want your fluid to be cooled. A lot of times it'll just pump up against the the pressure relief valve or the pressure control valve and just set the pressure at that. Either way, but directional control valves can either be electrically operated or mechanically operated. Okay. Cylinders. Now, cylinders are affected by the area. In this particular cylinder, if I'm pushing the cylinder from left to right, it will develop more power than if I'm pulling it from right to left. And the reason is the annular area on both sides of the cylinder. Now, it doesn't look like this rod is very thick, but this rod normally would be 12 millimeters, 19 millimeters. The cylinder itself might only be 50 to 100 millimeters. So it will be a significant amount of the area of the inside of that cylinder. As a result, there will be a reduction in the amount of force able to apply to the cylinder going this way as it is coming this way. Okay. More on that later. Okay, a flow control valve is designed to control the speed of something. Now, sure, there is a little bit of pressure drop across the restriction, but the idea is to provide like a gate to slow the fluid down. The fluid all gets in. Think of a turnstile in the subway. Everybody still gets on the train, it just slows the rush. Same kind of thing. The fluid is forced through this adjuster to the restriction, which can be used to control the speed. As a result, it will go into the cap end. This will control the speed in both directions. If it had a bypass valve on it, it would control the speed in one direction only. Well, more on those later. There's different types of flow control valves that you can use, right? Flow control valves all work by reducing the flow rate, okay? You can get you need a bigger pump, quite frankly, or you need an accumulator system in order to get more for less. But it's complicated, like in anything. It's much easier to just use a bigger capacity pump. The maximum flow rate is determined by the pump. How much fluid can be made to flow? That's your limiting factor. If the pump flow rate is 10 gallons a minute or 40 liters a minute, and the flow control valve reduces it to 6 gallons a minute or 30 liters per minute, then we have approximately 10 liters per minute being circulated through the maximum relief valve. And as mentioned before, that's an incredible waste of oil, and the flow control valves reduce system efficiency significantly. right? So what we can do in that condition is maybe we have a variable displacement pump. We have a pump that can pump at 10 gallons per minute when required, but can also throttle it back to 4 gallons per minute when required. And that's generally how we do things in hydraulics. It's the easiest way to do it. Okay, check valves. As mentioned, check valves allow fluid only in one direction. So they are usually spring loaded on this side, so the spring puts the ball up against the seat. If I push fluid in this direction that has a higher pressure than the amount of spring force, it will open that ball and let the fluid to come through until it had been equalized and the spring pressure is greater, at which point it will slam shut. Check valves are used quite often to prevent backflow. And also we'll use them in flow restrictions and speed devices to prevent backflow conditions. Also used in HVAC systems on heat pumps like mini splits to make sure that the fluid goes in the right direction, whether it's air conditioning or heating. Okay, pressure reducing valves. The pressure reducing valve job is to reduce part of the circuit. They're adjustable. The main system pressure is regulated by the maximum pressure relief valve. The mainline pressure passes through the PRV, normally open valve, and if the outlet pressure exceeds the preset, the valve will start to close, restricting flow. So this works in the opposite way that the pressure relief valve uses, right? This will start to close it off as opposed to opening it up. This crosses a pressure valve across the valve and allows the actuator to relieve less pressure, and then therefore it's reducing its output force. So these are very useful if you have to provide a constant load from a hydraulic system. For instance, you're bending a metal or something along those lines, and you don't want to have it, bend quicker in one spot of the hinge rather than slower in the other. So you may use a PRV in that case. We'll be getting into more of these valves and motor combinations later on in the presentations after we learn a few more of the schematic diagrams. And that is the end of this presentation. I hope you enjoyed it. Again, my contact information is on the syllabus. If you feel like reaching out at any time, please do. And we will talk to you next time. Have a good day.